Hey everyone, and welcome to The Explainer. Today, we're doing something really exciting. We're diving into the hidden rules that literally build our entire universe. That's right, we are cracking the code of matter.
So, think about this for a second. You know when you see a crazy chemical reaction, it's violently bubbling, fizzing everywhere? What actually happens to the mass of that stuff? Does it just vanish into thin air? Well, by the end of this explainer, you're going to see exactly how the universe tracks every single microscopic piece of the puzzle. No magic involved.
Here's our roadmap for today. We'll start with the laws of matter, then look at Dalton's atomic theory, how atoms bond together, writing chemical formula, and finally, properties and molecular mass. Let's get right into it.
Part 1. The Laws of Matter. Now, our understanding of all this didn't just happen overnight. It was kind of like a historical relay race of pure genius. Back in 1789, Antoine Lavoisier proposed the law of conservation of mass. Shortly after that, in the late 1700s, Joseph Proust gave us the law of definite proportions. And then, jumping to 1808, John Dalton tied the whole shebang together with his atomic theory. So let's see how this builds, starting with Lavoisier.
Check out this setup. We've got a conical flask filled with vinegar and a balloon tightly sealed over the top holding some baking soda. When you lift that balloon and let the baking soda fall into the vinegar, boom, you get this brisk effervescence. It bubbles up wildly and the gas inflates the balloon. But look closely at the digital scale. Before the reaction, it reads exactly 22,500 grams. And after the reaction inflates the balloon, still exactly 22,500 grams. It doesn't change one bit.
This perfectly illustrates what Lavoisier proved with his law of conservation of mass. Basically, matter can neither be created nor destroyed. The total mass of your starting reactants is always going to equal the final mass of your products. The universe never actually loses matter, it simply redistributes it.
Okay, but how exactly does it rearrange itself? Well, that brings us to Proust's law of constant proportions. This law dictates that elements in a chemical compound always combine in a fixed, unbreakable ratio by mass. And it doesn't matter where you found the compound or how you made it. For example, if you take a drop of purified ocean water or just a drop from your kitchen tap, it's the exact same. It'll always contain hydrogen and oxygen in a strict mass ratio of 1:8. It's like the ultimate universal recipe.
Moving on to Part 2. Dalton's atomic theory.
So, Dalton looked at these unbreakable rules from Lavoisier and Proust, and he asked the big question, why? His answer was atoms. These indestructible, microscopic building blocks. He realized that atoms of a specific element are perfectly identical in mass, and that they combine in simple whole number ratios. Because honestly, you literally can't have half an atom.
Which leads us directly into Part 3, how atoms bond together.
You see, atoms are driven by this singular microscopic desire. They just want to achieve a stable outer shell of electrons, what we call an octet. If they don't have a full shell, they're going to mingle with other atoms to get one. And this generally happens in two distinct ways. First, we have covalent bonds. This is where atoms act like partners, totally sharing their valence electrons to reach stability together. On the flip side, ionic bonds are a bit more aggressive. This is the outright transfer of electrons. One atom steals or gives away an electron, and that creates oppositely charged ions that magnetically lock onto each other.
You can see the difference in action right here. On the left, look at those two chlorine atoms. Each has 7 outer electrons and just needs one more to be happy. So by overlapping their shells and sharing a pair of electrons, they both achieve a stable 8. That's a single covalent bond holding them together as a chlorine molecule. Now on the right, look at the sodium atom. It has just one lonely electron in its outer shell. Instead of trying to share, it just completely gives that valence electron away. By losing a negative charge, it becomes a positively charged sodium cation, completely ready to magnetically lock onto a negatively charged anion.
All right, Part 4, writing chemical formula.
Now that we know how they bond, how do we write it down? Chemists use this brilliantly simple trick called the crisscross method. Step 1, you just write the element symbols side by side. Step 2, write their valency underneath. Step 3, cross them over. The valency of the first one becomes the subscript of the second, and vice versa. It's almost like a tiny puzzle.
Let's see this in action with these examples straight from our source material. Check out the formula for calcium chloride. Calcium, Ca, has a 2+ charge. Chlorine, Cl, has a 1- charge. When you crisscross those numbers, and we ignore the plus and minus signs here, the 2 from calcium drops down next to the chlorine, and the 1 from chlorine drops down next to the calcium. Now, we don't normally bother writing the number 1, so your final formula is just CaCl2. The positive and negative charges balance out perfectly. And you apply that same beautifully simple logic to aluminum oxide, which gives you Al2O3.
Now there is just one little exception to watch out for. Sometimes atoms cluster together and act as a single charged unit. We call this a polyatomic ion. A super common one is hydroxide, OH, which has a 1- charge. If you're crisscrossing a number greater than 1 onto a polyatomic ion, you absolutely have to put protective brackets around the whole cluster first. So if magnesium pairs with hydroxide, it's written as Mg, then OH in brackets, followed by a 2. This just makes sure we know there are 2 whole hydroxide groups, not just 2 hydrogen atoms. Makes sense, right?
Finally, Part 5, Properties and Molecular Mass.
Here's where it gets really cool. The way these atoms bond directly dictates the properties of the material that you and I can actually see and touch. Ionic compounds, like your everyday table salt, generally dissolve in water, but they won't dissolve in solvents like kerosene. Crucially, because they're literally made of charged ions, they can conduct electricity, but only when they're melted down or dissolved in water, which allows those ions to move around freely. Covalent compounds, however, like camphor or sugar, act almost completely opposite. They often dissolve in solvents like petrol, but not water. And because they don't have those charged ions, they just do not conduct electricity.
Another major difference is pure physical strength. Ionic compounds don't form isolated, independent little molecules. Look at this microscopic view of sodium chloride. The oppositely charged sodium and chloride ions attract each other from all sides, and they build this massive, repeating, tightly packed 3D grid called a crystal lattice. Because of these incredibly strong interionic attractions locking everything into place, ionic compounds typically boast seriously high melting and boiling points.
And this structural difference actually changes how chemists calculate mass. For covalent compounds, which exist as distinct independent molecules, we calculate molecular mass. You simply add up the atomic masses of the specific atoms in that one isolated molecule. So water, H2O, adds up to 18 units. But for ionic compounds, since they are an endless 3D crystal lattice and not just a single molecule, we calculate the formula unit mass. This is the sum of the atomic masses in the absolute simplest ratio of those ions. So for sodium oxide, Na2O, the formula unit mass is calculated as 62 units.
And that brings us to the end of our investigation today. We've traced the unbreakable laws of matter all the way down to the microscopic behaviors of atoms. We've seen how their quest for a stable electron shell essentially builds the compounds, crystals, and reactions that make up our entire universe. It kind of leaves us with a profound thought. You are also an incredibly complex system of these exact same chemical reactions. So I'll leave you with this. If the atoms in your body are just sharing and transferring electrons to find stability, what rules are you made of? Keep questioning, keep learning, and thank you so much for joining me on this explainer. Catch you next time.